on a question and we need to find the work done. This is a calculus question. We're going to find some work done here. Basically, we have a container of water, right? This is a container and this is water, right? The container is 10 meters tall and the water is 4 meters tall. Container is 12 meters long and 6 meters wide. And so how are we going to find the work done to move all of this water, right? All of this water right here. How are we going to find the work done to move all of this water up out of the top of the container? So basically to 10 meters. So let's think about the equation for work done first, and then we'll get there in a second. So work done is equal to work done is equal to force times distance. The force here we can decompose into mass. Force, we can think of it as a weight multiplied by distance. How do we find the weight? The weight is just mass times gravity times distance. I forgot to tell you in this question, we're going to use gravity equals 10 meters per second squared, and we're going to use the density of water as equal to 1,000 kilograms per meters cubed. So how do we find the mass? Well, we get the volume multiplied by the density, then that multiplied by the gravity gives us the weight, multiplied the distance gives us the work done. So basically, what we're going to have to do is find the volume of each slice and multiply each slice by the distance from itself to the top of the thing. So I'm going to show you what I mean, right? Think of it like this. I'm going to draw some slices of the water. This is going to be over exaggerated. Right? This is a one slice. This is the top slice, for example, and this is the second slice. This is the third slice, right? You see how there's different slices of the water, right? Each one has a different volume, therefore a different mass, different weight, and they also have a different distance to the top. If you look at here, this to here is 6 meters, right? 10 minus 4 equals 6. Meanwhile, the water slices, let's say at the bottom, well, what is their distance from the top? It's going to be 10 meters. So we need to find a way to relate the mass of the slices to the distance away from the top. So let's think of it like this. I want you guys to plot the shape of the container. Something like this. Does that make sense? We're gonna do it. We're gonna use the x because we're gonna be integrating with respect to x. So let's use x as the height, for example, the height of the blocks. And we can forget this axis. I just want you guys to think of it like this. Okay, so the water, this is 0, this is 10 meters, right? This is the top, this is the bottom of the container. And let's say our water is here. Let's use blue. The water is here, which is at 4 meters. So first of all, we want to split it. If we want to make slices that look like this, right? Slices with different distances to the top, we want to split this shape into something like this, right? So in this case, this length here is dx. And then therefore we can find the volume using that. So how do we do that? Well, if we think about it, what we're doing is we're slicing the water into chunks like this, rectangles. When we do it small enough, it's turning into rectangles, which makes the volume a lot easier to deal with. Dx is this width here. What is the height? Well, we're going to think about that, and we're going, and this is 12 meters, right? Yeah, 12 meters. Kind of, if you think about it, 12 meters is the length of the container, like that. So this slice would be 12. But I want you to think of it as if we're um, cutting the container in two. We're removing this part here. So if we think of it like this, let's just work with half the container. We'll work with half the container, so it looks like this. And whatever volume we get, we just multiply by 2 to get the amount of water, right? So let's say the water here is 4, this is 10 meters, this is 4 meters, and then we're cutting our water like this, which will look like, let me make this diagram better, kind of like this, slices that look like this. But basically, you can imagine it, right? That is technically what the container looks like. We're just missing the upper half. So how are we going to do this? Let's find the idea of this line. So if we know that let me remove these lines first. But if we know that the container is 6 meters wide, right? We know that if we go back to our original thing, 6 meters wide, if we split it in half, well, this length here is only 3 meters. So we can think of it on this cross section here, this height, oh, not this one. When we split it in half, this height is just half of 6 meters, which is 3 meters, right? So therefore, there's this equation here. Let's do it in red. This equation here that tracks this side of the thing, right? So if I'm going to draw another graph here. This is without the 3D. So let's say this is X. This is without the 3D. It's just completely in 2D. That's the shape of the container, right? This is the water at 4 meters. This is water here. We're splitting it in this size. And this right here has a height of 3 meters. And the equation continues indefinitely, just like any equation. And this is at 10 meters. So how do we find the equation of this line, right? Well, simple. At x equals 10, y equals 3. So that would mean that if y equals kx, right, and 3 equals k times 10, remember x equals 10, y equals 3, then k would be equal to 3 over 10, and therefore this line has an equation of y equals 3 over 10x. That's it. So we have the equation of this line, and this line is going to give us the height at each x. So let's say that we took an x. Let's say that we took an x here, right? And we're working with this slice here. What is that going to look like? Well, okay, I'm going to remove this. I'll move this up top if we need it again, but I don't think we'll need it. So let's look at that slice there. So let's think of that slice as this, right? That's the vertical thing, and then this is the line. This is what its slice is going to look like. It's going to look like a rectangle. Remember that the actual container has another half here as well. Oh, hey Jeremy. So we cut the container in half. So now we have two. This is only half thing. So we actually have two. So when we find the volume, of, so keep that. When we find the volume here of this slice, we have to multiply by 2 to find the total volume of one slice. Total vol of one slice. Does that make sense? Okay, we'll get there in a bit. So let's ignore this one for now. I'm going to delete it here. Let's ignore that one for now. Just keep in mind that we're working with half. What is the length here? This is going to be dx. If you don't know this, check my other videos. And the length of this side here would be 12 meters, because that's the length of the container, right? So the only thing now we need is this height. What is the height? Well, the height, we can think of it as just the height of the equation at x, right? Let's say this is a second x, this is x2, well, the height at x2 would be here. So it's whatever the equation is at x. What does that mean? X, the height, is just equal to f of x, or it would just be equal to y, the y value of x. And we know here y is equal to 3 over 10x. Therefore, 3 over 10x equals the height. And now what's the volume of one of the slice? The volume of half slice, because there's 2 slices in every slice, the two halves in every slice, would be equal to, it would be equal width times height times length, right? The width is dx, height is 3 over 10x, and the length is 12. Therefore, what we have is like 12 times 3 over 10 x dx, or it would be, I'm terrible at mental math, 18 over 5, I think, 18 over 5x dx. Because 5 cancels out, 2 cancels out there, so it's 6 times 3, 18, yeah, 18 over 5x dx. 18 over 5x dx. Okay, so now that we have the volume of one slice, half slice, sorry, we have to multiply by 2 really quick to get a volume of a full slice full slice, which equates to one of these slices, remember, because we cut these in half, basically. So a volume of the full slice would just be equal to 36 over 5x dx, okay? So now let's think about this. The work done is equal to force times distance. Force is equal to the mass times by gravity times by distance. That's work done. And mass is equal to volume multiplied by density multiplied by gravity multiplied. So we have the volume here. Let's say the work done for slice. And this is slice at x, right? So for a slice at x, the work done is equal to its volume multiplied by density multiplied by gravity multiplied by distance. So let's do all the things before distance. What's the volume? The volume is equal to, let me just try to go up here, minus 36 over 5x, right? 30 sorry, not minus, 36 over 5x dx. What's the density? That's 1,000 kilograms per meters cubed. Multiplied by gravity, that's 10. I'll put this down here, meters cubed, 10 meters per second squared, multiplied by distance. So if we think about it, it would just be 36 over 5 times by 1,000 times by um let me just think. So let's take the 5 out. So 36 multiplied by 1,000, and then 10 divided by 5 will be equals to um x, sorry, yeah, x dx multiplied by d. I think that's the correct answer. This would make 72,000 x dx multiplied by distance. So this is work done to move one slice at x. So what's the distance from this slice to 10 meters? Well, if we think about it, what's the distance, right? Here, this x here, x equals 10 meters, right? Is exactly where we need to get. And this is the distance we need to travel. How do we find that distance? Well, let's think about this. That length there. This length here is x. This is the distance, and this long length here, let's do it in yellow. This length here is 10. Well, if we take 10 and we minus x, so we minus this part of it, then that's equal to d, right? The distance from x to 10 meters is just 10 minus x. So distance here would be equal to, let's just rewrite the equation, the distance is equal to 10 minus x. And this is our equation for the work done of one slice at x to 10, right? Which is equal to 72,000 multiplied by 10 minus x multiplied by x dx. And now once we have one slice, right, we have this slice. Let's say we have this slice done. We just need to add the work done to do this slice, to this slice, to this slice. Basically what we're saying is that we need to sum. We're going to use the integration sign as a sum. So let's say we sum the work done of each slice. And where each slice at x, and x ranges, we know where x ranges from. It ranges from 0 to 4 here, right? Because that's the height of the water in here, from 0 to 4. So we're just summing the work done for each slice at x. And x exists from 0 to 4. Okay, now what does this mean? Well, we replace the summation sign with symbol with this integral sign. We go from 0 to 4, and we do the work done for each slice. What's the work done of each slice at x? Well, the summation of that is just here, 72,010 minus xx dx. So then that would be equal to summation from 0 to 4 of 72,000 10 minus x, 10 minus x dx. 10 minus x dx. Yep, that's it. We take 72,000 out from 0 to 4 10x minus x squared all multiplied by dx. And then that will give you the answer of the work done, which I've done above. I've done this last night to check if the answer is correct, and the answer is, did we get it? Yep, so we got, yeah, basically 72,000 from 0 to 4 of 10x minus x squared dx. And the answer, once you do all the math out, is 4,224 joules. 24,000 joules. So yeah, that's it. Thank you guys for watching. I'm gonna head to my ECE class now. I'll see you again later.